We are already very familiar with Newton's second law that the resultant force acting on the object in a vector form equals to m, its mass, multiplied by its acceleration a, also a vector that has the same direction as the resultant force. And also from kinematics, we know that acceleration is defined as the time derivative of velocity vector. Therefore, by combining these two equations and multiplied dt to both sides of this equation, and now we can integrate both sides of this equation for a process from state 1 to state 2. On the left-hand side, this expression is integrated from the initial time t1 to the final time t2. On the right-hand side, the expression is integrated from the initial velocity v1 to the final velocity v2. And the right-hand side equals to mv2 minus mv1, since m is a constant. And we can define a new parameter to replace this mv. It is known as the linear momentum. L equals to m times velocity v. L and v are both vectors.
See how she actually just defined the equation we were just looking at, which is, well, this is for particles, for a system, which is that equation right there. Our impulse is equal to the difference in our momentum. That's the same equation she just defined. Newton's second law, substitute into, I guess, kinematic equations. Acceleration is equal to the change in velocity with respect to time. Substituting that in and continuing through.
So Dave?
Yes.
Yeah. Quick. So is impulse, is that the fourth derivative?
Oh, interesting.
Position, velocity, acceleration. Cat called it the jerk.
Oh,
or is that third derivative?
Third derivative.
Third. That's not.
I do not believe so. How's that?
Okay.
But I could be wrong. There could be a relationship that I'm unaware of. I do not believe so. This is purely mass times velocity.
Okay.
Momentum is mass times velocity, so there isn't a jerk involved.
Okay.
That I know of. However, there might be a relationship that I don't know. And whenever I say something absolutely, I'm always proven the student will come in a week later and say, "You said this." Okay, I'm wrong. So I've learned not to be absolute when I don't know what I'm talking about. I do not believe so. How's that? This should be related to mass and velocity. And back in our engineering physics days, we did use an L for momentum. In fact, we would have L2 minus L1, that would be equal to our impulse. Impulse is the change in momentum.
And for the left-hand side, we can define a new parameter as well to replace this integration term, which is called the linear impulse I, which equals to the integration of a force with respect to time for a process. Therefore, the previous equation can now be written as the principle of linear impulse and momentum. The summation of I, which is the total linear impulse caused by external forces associated with the process from state 1 to state 2, equals to the change in the particle's linear momentum, L. Here, we need to emphasize the word linear because we will learn about angular impulse and angular momentum later. You might notice a similarity of this equation with the principle of work and energy. Despite the similarity in the format of these two equations,
in the last chapter,
the left-hand side of these two equations are parameters both caused by external forces, and also they are both associated with a process. For the right-hand side, the two parameters are both associated with the state of the particle. The difference is, as you can tell, that the principle of work and energy is a scalar equation. Both work and energy are scalar properties. However, the principle of linear impulse and momentum is a vector equation since both impulse and momentum are vectors. The principle of linear impulse and momentum is normally written in this way to show a direct relation of how external forces are changing the velocity of the particle. And because this is a vector equation, it can be rewritten into 3 scalar equations along the x, y, and z direction respectively. The principle of linear impulse and momentum can also be applied to a system of particles. Here, the total impulse term includes all the impulse caused by external forces acting to this system, and for the linear momentum term, m is the total mass of all the particles in the system, and vg is the velocity of the mass center of the system. Let's revisit this slightly modified example that we worked on before using equations of motion. Here, we have 3 toy cars connected together. They're being pulled by a constant force of 3.5 Newton, and we need to determine their velocity after 2 seconds. Now, for this problem, we're looking at a direct correlation of a force, time, and speed. In other words, we know that this force of 3.5 Newton has been applied to this system of cars for 2 seconds, and we want to find out how that changes the velocity of the system. Therefore, the most
And you're used to doing that with what we have done before, but now we're going to look at it from a momentum perspective rather than from an energy or from a force and kinematics perspective.
ideal way to solve this problem is by applying the principle of linear impulse and momentum, since that provides this relation between force, time, and speed. We still start with the free body diagram of this system, but since there is only motion along the horizontal direction, therefore we only need to write the principle of linear impulse and momentum in a scalar form along the x direction. Substitute in the information. The initial velocity is 0. The force is constant, therefore its impulse on the system is simply determined by its magnitude 3.5 multiplied the time, 2 seconds, and that equals to the total mass of the system multiplied by the final velocity, which is our unknown. So from this equation,
If you think about it, you've got 2 seconds and you have a constant force being applied. So if we did a force versus time graph, it would be very simple. It would be a constant force of 3.5 newtons and over 2 seconds. So it's a box, 3.5 tall, 3.5 newtons tall, by 2 seconds wide. Multiply that, and that's, so our integration was easier because of that. It was just a simple box, so we didn't have to go through and find an equation for that. And then integrate that. And we will be doing the same thing on our homework, actually. Our homework is areas underneath curves that we can solve by triangles and boxes.
we can simply solve Vx2 to be 20 meters per second. I encourage you to try to solve this problem using equations of motion and compare the methods to see which method is simpler.
This is so much faster. Take a look at that. You had 0 initial momentum, 0, and then you had a change in impulse. You added a certain amount of force over a certain amount of time, right? That's 3.5 newtons of force for 2 seconds. And that's going to equal your final momentum. Your final momentum is the total mass, just add up all the masses, and times the final velocity. We don't know the final velocity, but you know what? I can take that mass, which is 0.35, divide both sides by 0.35, and suddenly I have solved for my velocity. Look at how quick that was to solve for. So there are other ways using, there's other methods for us to solve for these things.
So they're giving you the mass, right?
The mass of each of those pieces,
Yeah.
and that was actually in the previous graphic.
Oh, okay.
Yeah. Let's go back.
Its magnitude 3.5. Most ideal way to solve this problem is by applying the principle of, we can simply solve Vx2 to be 20 meters per second. I encourage you to try to solve this problem using equations of motion and compare the methods to see which method is simpler. Let's revisit another example. For this problem, we need to determine the power of the force at time equals to 6 seconds. And power is determined by the magnitude of the force multiplied by the velocity. And if you recall, when we first solved this problem before, we used not only equation of motion, but also kinematics. Here, let's try to solve this problem using the principle of linear impulse and momentum. So we still start with the free body diagram of the crate, and we still need to determine at what time motion starts. In other words, we need to determine at what point the maximum static frictional force between the crate and the surface is overcome. And as you can see, here we have exactly the same approach to determine this time using equilibrium equations. And you might argue, how come we don't apply the principle of linear impulse and momentum here? I want you to be careful when you're working with static frictional force, because here what we have is only the maximum static frictional force. If you remember, static frictional force is not a constant and is always determined through equilibrium. After motion has started, since there is only motion along the x direction, we can write the principle of linear impulse and momentum along the x direction only in scalar form.
Another way to look at
I
what
want you
she's
to
saying
be kept.
is, this is before motion has started.